Okay, let's start. So, have you tried assignment 2? Started yet? Have you started? Yeah. Okay, so how many features have you finished? Okay. Okay. And, okay, let's start. Anyway, this is our last lecture for this course, this term. And if you open the lecture slides page on WebCMS, you may see this. This is an error, depends on your browser. But it's only because you cannot see the embedded web page from this website. And you should click on View in the browser, this button here. You should click on this button to view the presentation, because I'm using a different website to make this presentation. It's not workable on Windows 10. Oh, sorry, it's not viewable on WebCMS. Sorry, I forgot to change the visibility. So can you see it now? Refresh the page. So yeah, but if you just have a look at the WebCMS page, you will see this error depends on your browser, and it's because this page cannot be embedded in another web page. So you have to click on View in the browser to view this to view the slides. So today is our last lecture, and we will going to have a recap of what we have learned. And this is like a graph of knowledge. It's not exactly a knowledge graph of what we have learned, and different colors have different meanings here. And we will go through all the contents we have learned for this term. So First, we started with an introduction to software testing, and we covered these topics. So first, this course is not just software testing, it's software testing and quality assurance. So talking about software quality, what we care the most is the dependability of software. And we covered 4 concepts related to dependability: correctness, reliability, safety, and robustness. And we revisited these concepts when we learn when to stop testing, right? We need to make sure that our software is reliable, so we could have some measurements for reliability. So this is software dependability. And after that, we learned the concepts of verification versus validation. So, are we building the product right? Is this related to verification or validation? Do you still remember that? Are we building the product right? It's actually related to verification. Are we building the right product? Is related to validation. And then we learned dynamic analysis versus static analysis. So testing is considered as a dynamic analysis technique because we need to execute the program and observe for the behaviors, for abnormal behaviors. And for static analysis, because we don't need to execute the program, we just need to scan through the code and look for some patterns. So it is called static analysis. And after that, we learned 6 basic principles for doing testing. So can you still remember these principles? So you don't have to recite all of them, but when you see each one of the term here, you should be able to explain the concepts behind. So for example, for sensitivity, it's actually related to a dry sanitizer we have learned. So we should increase the sensitivity of capturing errors or bugs. For visibility and observability, for example, we should make sure that our testing progress is observable, so we can make sure we can check the progress of testing. And for partitioning, partition means we should partition big problems into smaller ones, and that is actually the key mechanism of gray box fuzzing. So that's all about the introduction to software testing. And after that, we learned the first basic concept, or the first fundamental methodology in testing, and that is functional testing. So for functional testing, first we learned boundary value testing. So do you still remember what is a normal boundary value testing? What is a robust boundary value testing? Do you see? Okay, good. And what about worst case boundary value testing? The single fault assumption. So single fault assumption means that each time, if there are multiple parameters, each time we should only allow one parameter to take the invalid value, and the rest of the parameters should take the normal values. And for worst case, and in the worst case boundary value testing, we allow multiple parameters to take invalid options. So this is boundary value testing. And then we also learned equivalent class testing. So similar to boundary value testing, there are concepts of normal and robust, weak and strong. So weak and strong is related to the single fault assumption. And then we learned the last type of functional testing, decision table based testing. And there are some key concepts. For example, in a decision table, what is a stop? What is an entry? What is an action and what is a condition? And we also learned that decision tables could either be limited entry decision tables or extended entry decision tables. So do you still remember the concepts of limited entry decision tables? Yes? Okay, good. So limited entry decision tables means that each one of the entry could be either only be true or false. But extended entry decision tables means that the values could take more than just true and false, could take other options. And that's all about functional testing. And functional testing is also known as black box testing techniques, because we don't really need to have access to the source code of the program. And so that's why the key of, so what we can only deal with the inputs, the testing inputs. So the key of all these functional testing techniques is how should we divide the input space. For example, we can use boundary values to divide the input space. We can use equivalent classes to divide the input space. We can use the relations between actions and conditions to divide the input space. And after that, if we have source code, we learned structural testing. So we can do structural testing. And structural testing is all about different coverage metrics. So first we learned statement coverage, which is basically to cover all the statements. We are trying to cover all the statements of a program. But covering all the statements doesn't mean the program is bug-free, because we still have branches to cover. So branch coverage is the second coverage metric we learned. And in order to learn this concept, we learned the concept of control flow graph. So a control flow graph is made up of basic blocks and edges or transitions between basic blocks. And the target here is to execute all the true and false branches for a program in a control flow graph. And after that, we learned condition coverage. So what's the difference between a condition coverage and a branch coverage? Do you still remember that? So it's not in assignment 1, so you may not have a very deep impression. So condition coverage means branches are related to conditions, but not all conditions are used in branches. So there are some conditions which are not used in branches, and like the values of true and false, maybe they are only like there are some special value assignment statements related to conditions. So for condition coverage, we only care about the true and false of all true-false values of all the conditions, and we don't care whether they are used in branches or not. So this is so condition coverage covers branch coverage, and we have encountered one additional type of condition coverage, which is called modified condition decision coverage. So you can click on this link to have a look at the the related slide, but I tried to add links to all these items here, but it turned out that I need to add a link to every one of them. So it's better if you just go to the related slides and have a look. So the last type of coverage we learned is path coverage. Path coverage does have the problem of path explosion. So when is there a path explosion? Normally, loops. Yes, loops. So whenever we have a loop, whenever we loop the loop for a new round, then we will have a new path. So if we have loops, we will have the problem of path explosion. We will have too many paths. And in order to do this, to make this, because normally achieving 100% of path coverage is not doable in real life because of this path explosion problem. So we have to handle loops with some strategies, and that's why we learned some partitioning coverage, some partitioning technique to do this. So first we learned boundary interior coverage, which is related to the condition values of the loop, and then we learned loop boundary coverage, which is related to how many times we go through a loop. And then we also learned linear code sequences and jumps, which could have multiple levels. And if it is at level 1, then it is essentially statement level coverage. If it is at level 2, then it is branch coverage, and so on. And we also learned that, do you think if we achieve 100% of, because path coverage is very strong, we are trying to cover every possible path in the control flow graph, every possible execution path. So do you think achieving 100% of path coverage means that the program is bug-free? No. The answer is no. We have learned it with the last question in assignment 1. So you can create something that is, although the test suite can achieve 100% of code coverage, path coverage, you can modify the program to inject an error which is not detectable by the test suite, right? So 100% of code coverage, the path coverage is still not enough, because it's only about control flow, and we need to have some knowledge about the data flow. Data flow is related to how the information on how the value is transferred from one parameter to another. And we learned that we should care about def and use and the coverage of def-use pairs when we do data flow related testing. But data flow is not the key in this course, because there's another course covering this topic. So that's how all the different types of coverage we have learned for structural testing. And you can see that we are increasing the costs if we want to collect more detailed coverage. And structural testing is also known as white box testing, because we have access to the source code and we try to dive into the source code and collect coverage feedback. And structural testing, the key of structural testing is about which coverage metric we use. And after learning functional testing and structural testing, we encountered the third fundamental concept, which is called different levels of testing. And first, we learned the V model of testing. So it is related to how do we map software development life cycle with our testing life cycle. So you can see that unit testing is more detailed. It's closer to the developer, how we do the implementation, and integration testing and system testing are more related to requirement design or architectural design. So we have learned 3 different levels of testing. The first level is called unit testing, and it is considered to be done normally by the developers, and it is actually the basis of test-driven development. And then we also learned integration testing, and integration testing is all about how do we do this integration. So there are multiple strategies to do integration. So we could do decomposition-based integration. For decomposition-based integration, we can do top-down integration, we can do bottom-up. And if we combine top-down and bottom-up, we can do sandwich integration. And there's also an integration strategy called big bang integration, which is very close to system testing, but there are some minor differences. And we also learned call graph-based integration. Do you still remember what is a call graph? A call graph, yes, good. A call graph is actually the relations between different functions, which function is calling another. So with a call graph, we can do pairwise integration. We can try to cover all the edges in the call graph, and we can also do neighborhood integration, which is to cover some neighbors for array function. And we also have path-based integration strategies. And for system testing, we learned multiple types of model-based testing techniques. And there are many different models, and decision table is one of them. And can you come up with another model for modeling programs? Finite state machine is very common, actually. It's also very common, a finite state machine. And we also learned some non-functional testing techniques. For example, we learned performance testing. We learned usability testing. We also learned the concept of compatibility testing. And these are all system-level testing techniques. And for integration testing and system testing, they are normally done by an independent testing team, not done by the developers. And after that, we learned test scaffolding. And this is the structure of a test case. So do you still remember the concepts of each component here? Like, what is the difference between a driver and a stub? We have a quiz question for that in quiz 1. And okay, so and also for some programs, tear down is also quite important, because some functions may have side effects, and we have to remove that side effect. So this is about test scaffolding and levels of testing. And after learning these fundamental concepts, we learned our first practical technique in this course, which is called fuzz testing, or we focus more on gray box fuzz testing. So for fuzz testing, it could also be categorized as black box, white box, or gray box. So for black box testing, there are two types of black box testing techniques. The first one is mutation-based fuzzing, and the second one is generation-based fuzzing. So do you know the difference between these two? So mutation testing means that we are creating new test inputs by mutating existing seeds. And for generation-based testing, means that we are generating the new test inputs from scratch. So we don't have a seed to refer to. So this is called black box fuzzing, which means that we don't collect any internal information of the program. And for white box fuzzing, it is often referred to as symbolic execution. And symbolic execution suffers from the problem of path explosion, because we are trying to cover every path of the program by solving the constraints we have collected along the path using some constraint SMT solvers. And in order to solve this path explosion problem, we have introduced the concept of concolic execution, which is to combine concrete execution with symbolic execution. And this is white box fuzzing. As you could imagine, this is very heavyweight analysis, so we can't do it on very large programs. And in order to have both the advantage of scalability and effectiveness, we introduced the concept of gray box fuzzing. And the key mechanism is to divide and conquer. So we are trying to divide the search space of the program state using the seeds using new seeds we keep during this fuzzing process. And there are several key strategies we need to care about when we do gray box fuzzing. And they are seed prioritization, which means that which is related to which seed should we collect next. And power scheduling, which is related to after collecting one seed, how many new test input should we generate based on this seed. And after that, we also learned how could we generate new test inputs. And this is a very, very practical technique for detecting vulnerabilities in real-world programs. And we learned one of the arguably the most favorable or the most popular gray box fuzzer, which is called American Fuzzy Lob, and you are doing mini lob for your assignment too. So this is the first practical technique we learned this term. And after that, we learn the concepts of software complexity. Software complexity is useful for testing because normally we believe that the more complex a piece of code is, the more likely it is buggy. So it can help us to prioritize our testing targets if we can analyze the complexity of a piece of software. And like different levels of testing, we have different levels of complexity. First, we have unit level complexity. And we learned two complexity metrics. The first two set of metrics. The first one is called cyclomatic complexity. It is related to branches and loops in the control flow graph. or call graph. So do you still remember the formula to calculate this? For a graph, edge minus the number of edges minus the number of nodes plus 2. Yeah, and we do have a fast calculation formula which is related to the number of ifs, number of cases, number of loops, and the number of exits, right? So this is about cyclomatic complexity, and we also learned house-tied matrix, because cyclomatic complexity only cares about the branches and the loops of the program. And if we have a very large linear procedure in our program which has no branches at all, then it should be more complex than a small piece of code, right? A small linear piece of code. Then we should think about some matrix, complexity matrix, which cares about the volume of the program. And therefore we have house-tied matrix, and it is made up of several formulas. And you should be able to calculate them and based on the formula. And after that, we learned integration level complexity. We learned the cyclomatic complexity for call graphs. We learned object-oriented complexity matrix. And particularly, we learned something related to coherence and cohesion. And after that, we learned system-level complexity. Actually, for system-level complexity, it is actually made up of those unit level and integration level complexity. We don't really have a definition for this, but system level of complexity analysis is important because we can use this complexity analysis to prioritize our testing targets. And that's all about software complexity. And then we started to learn a new concept called test oracles. And test oracles is useful for testing because for testing is all about generating test inputs, execute them, and observe for abnormal behaviors. And test oracle helps to tell us which behaviors are abnormal. So it is like the judge for the observed behaviors. And for testing oracles, first we learn specified oracles, which is normally human created from the requirements. And we can specify oracles according to some models, system models. Like, for example, for some finite state machines, there could be an error state. And if the program goes into the error state, it means that there's something wrong. And we can also use expected values as oracles. For example, all the assertions you write in unit tests. So we can expect a value from you can expect a return value or maybe an internal intermediate variable value for us, and then we can compare the actual value with our expected value to tell if there's anything wrong. So this is how we can create oracles with expected values. And we can also use self-checks. For example, we can, for some programs, when we write the code, we can raise exceptions. We can add assertions in our code. When we write the code, not in the testing code, we can add assertions or raise exceptions in our code. And this can also help the tester to create test oracles. And apart from manually written test oracles, we can also derive test oracles automatically. And we have learned several so-called testing techniques which are related to this derived oracles. I think there's a typo here. We learned 3 testing techniques. So first, differential testing. So do you still remember what is differential testing? Why it is related to test oracles? Huh? Okay. So the differential testing is actually related to having multiple implementations of the same design and compare the execution results. And because they are the implementations for the same design, they should behave the same, right? And if there's a difference between their behaviors, then it means that one of the compared implementation must be wrong. This is differential testing, and it is very useful in practice. And we also learned regression testing, which is related to reusing existing test cases to test out our newly updated features. So, for example, if we have already maintained a test suite, and if we changed some features in our program, how should we plan our testing? So we can reuse those existing test cases to do this. And then we also learned metamorphic testing, which is a very popular technique for creating test oracles. And actually, the inventor of metamorphic testing is currently in Australia, and this metamorphic testing is related. The key concept here is metamorphic relation. So it is an observation between different parameters and different program outputs. So do you still remember this concept? Okay, good. So metamorphic relation is to, for example, if we have a program, if we have written a function to calculate sine pi, and we don't know the exact value of sine pi, but we sine x. So we don't know exact value of sine x, and we can't use expected values to test out whether the output of the function is correct or not. But we know the relation that sine x should be equal to sine pi minus x. So we can write test cases to test out the results between sine of the function with sine x and sine pi minus x. If the results are different, then it means that there's something wrong with the implementation of the function. So we are trying to use some kind of metamorphic relations to check, to infer if there's an error in the program. So this is the key of metamorphic testing. And after that, we learned some implicit oracle. Derived oracle is actually particular to the testing target, as we just learned. And an implicit oracle is about the testing oracles, which is applicable to almost all the programs. For example, if a program crashes, then it means there's something wrong. And the key of implicit test oracles is sensitivity. So we can use some sanitizers to increase the sensitivity of this type of oracles. And we learned address sanitizer, and you can actually use it when you do testing with C or C++ programs. It is very easy to use. You just need to add one. You just need to add one compiler option in your compiler flags, and then you can use it. So this is implicit test oracles. And last but not the least, we also learn human oracles. Human oracles is different from the specified oracles. It is purely like using human to judge whether a program's output is correct or not. And there are some crowdsourced platforms for you to do this outsourcing of oracle labeling tasks. And this is particularly mentioned here because it is now kind of popular because of the large language models, and almost all the data of large language models, the human feedback reinforcement learning, right? The human feedback is actually done by crowdsourcing. And that's all about test oracles. And then we learned another concept of mutation testing. And this is not a new testing technique, not a software testing technique. It is actually a special technique that could evaluate the quality of a test suite. So for example, if we are trying to evaluate the quality of a program, we can create a set of test cases. And what if we want to evaluate the quality of this set of test cases? What should we do? We should create a set of target programs, right? And the way of creating the target programs is to mutate them, to add small changes to the programs, to generate new programs. And the newly generated programs are called mutants here. And can you still remember the concept of killing a mutant? Yes, good. So if the test case behaves, if the test suite behaves differently in the original program and the mutant, then this mutant is considered killed. So do you still remember the live mutants? Yes? Okay. So live mutants are those mutants which are not killed by any of the test cases in the test suite. And what about mutation score? Yes, is the ratio of how many mutants are killed. And the higher the score is, the better the quality of the test suite is. And we can also, in real life, if mutation testing is also quite useful. And if we try to analyze the live mutants, it can help us to expose the problem of the test suite design. And then we can also check the relative locations related to live mutants. So to check out what are the potential issues in those regions of the program. So this is how we can make use of mutation score and live mutants. And we also learned a set of mutation operators, which could be applied to the programs. And the ultimate goal of these mutation operators is to simulate the errors made by the programmers during the development. And we also learned about the quality of the mutants. So a mutant could be valid, could be invalid. A mutant could be useful, it could also be unuseful. And this is a question in quiz 2. So, okay, let's continue. Another concept we learned is when to stop testing. Not after this course, when to stop testing. So we should measure reliability of the program. So the ultimate goal is to achieve dependability. But among those 4 properties, reliability is the most suitable one for measurement. And we have learned different metrics for measuring reliability. We have learned probability of failure on demand, which is the number of failure divided by the total number of requests. And we also learned availability, which is related to the uptime of the system. We also learned the rate of occurrence of fault, which is how many faults do we encounter in a period of time. And we also learned mean time between failures. And in order to measure this reliability, we can do statistical testing. We can observe, we can obtain the operation profile of a system to observe which part of the feature or which part of the code is used more frequently by the users. And then we can create test cases or design the testing strategy to emphasize those frequently used features, to do statistical testing, to estimate, to collect information about all these 4 metrics, and to measure the reliability. And if the system is reliable enough, we can stop testing and release the system. And after that, we learned another practical testing technique, which is called combinatorial testing. It is actually a black box testing technique, and it is actually a system level of testing. And for combinatorial testing, we learned the concept of T-way combinations. And we learned from a report from one of the US government agencies. So what is the optimal value of T normally? So 1 or 2? Yeah, 2. And we'll also learn the concept of covering array. So we don't have to create a very comprehensive we don't have to create a test suite to cover all the possibilities, because there might be some redundancies, and we can create a covering array to get the minimal set of test suite that can achieve T-way testing, 100% of T-way coverage. And calculating this covering array is not it's not very straightforward. And we learned one of the algorithms, which is called greedy algorithm, how to calculate the covering array. And after that, we learned some advanced algorithms which could benefit these practical techniques. For example, just now we mentioned covering array. It could actually be calculated with genetic algorithm. You can think about it, how to design this algorithm based on what we have learned, but it is not required in this course. So for advanced algorithms, we learn how to model the testing as a search or optimization problem. And we learn several advanced algorithms. For example, adaptive random testing. For example, genetic algorithm. We also learned epsilon greedy algorithm, which is related to solving the problems of multi-armed bandits. And that's all we have learned for this term. So thank you for joining this course in this term. And this is the overview of what you have learned. And you can play around with this page. You can zoom in and zoom out and see what's going on. And the right circle here is the introduction. And the dark blue ones are the fundamental concepts. The green ones are those concepts related to testing which can help testing. And the purple ones are the practical techniques. And this golden one or the yellow one is advanced algorithm which can benefit the practical techniques we learn. So these concepts are mostly covered by assignment 1. These green ones are mostly covered by the quizzes. And this purple one is covered by assignment 2, which is considered more important. And also the yellow one is partially reflected in this purple one. So this is an overall structure of all you have learned. And I hope you can remember this even after this term, even after this course, after you finish all the assignments. And that's all. Thank you for coming, and thank you for joining this course in this term. Thank you. And this is our last lecture. And on Thursday, I will be offering some consultant for assignment 2. You can find me in my office if you want. Thursday. Yeah, same time.
Earlier today, but I don't have access to this thread here. So this is related to the empty one.
Oh, I will copy a screenshot. I'll put a screenshot here.
Okay.